Hey there, and welcome to the 63rd Tech Talk. 63. Well, it's just one shy of a power of two. My name is Julian. Hi, I'm Jay from Team Google here at Cybert Media. And it is my absolute pleasure to introduce to you today Adrian Ulges, who's virtually here with me. And he's a professor from the RheinMain University of Applied Sciences in Wiesbaden. And he will be telling us quite a bit about transformer networks today. We'll be starting with some fundamental concepts and then also some common architectures. I heard he'll be talking to us about BERT, which, of course, as somebody close to the Google ecosystem, is always interesting to me. Have some outside perspective on that. And the GPT series, which I'm sure lots of people have heard about in various formats, news formats, and some deep learning practice and tooling as well. So very, very interesting topics indeed. If you're ready, Adrian, take it away.
Yes, thank you very much, Julian. Well, welcome from my side to this talk with a catchy title, Transformers Revolutionizing Automatic Text Understanding. So catchy title and catchy topic, because transformers are actually amongst the go-to models in AI these days. And so here I brought you as a first slide kind of a motivation indicating why this is or how this is. Because this is an announcement of NVIDIA's flagship compute server, so the DGX series. And this here is a slide from April where they announced the new version, the DGX H100. And you can actually see that this GPU server has a particular transformer engine. So basically there's hardware being built for transformers, which kind of indicates how key this model is to AI research these days. Right, so there's even specialized hardware to speed up this particular kind of model. So in this talk, I'll try to clarify what all the fuss is about. So first section will be transformers. How do they matter in practice? I'll very briefly outline where they come from. So I'll give you like an outline of NLP research that has been taking place in the last decade. And then we'll go into nuts and bolts and kind of talk about the core mechanism at the heart of the transformer, which is attention. We'll talk about common architectures, indicating what you basically can do with this type of model. And finally, I'll outline some of our research that we are doing with this type of model in Wiesbaden. Okay, but let's motivate a bit first. So why do transformers matter? Transformers, even though they have been applied to to time series data and image data and other types of data recently, they actually come from the text domain. So this is basically a talk about natural language processing, or NLP, which is, it's kind of a term subsuming any applications that are about interpretation of text or dealing with semantic analysis of text. And well, there's a variety of tasks and applications to that. So you can see in the first line, there's a lot of core tasks at the heart, certainly information retrieval, which is basically text search. You can think about AI systems that answer textual questions uttered by a user. You can think about conversational agents. You can think about extracting information from text, like what are entities that are being mentioned, or what facts can we extract about these entities. And this leads to lots of exciting applications. So the second row is called general applications here. These are things like web search engines or personal digital assistants. So think of Alexa or these kinds of things. But there's also kind of industry-specific applications. So if you think of search, for example, we're all very used to getting very good search results from Google on the web, which is because these search engines learn from lots and lots of user feedback. But if you're in an industrial setting, like we're dealing with company text search, you usually don't have that feedback at that large scale. And it's more about analyzing the text itself, really. Right? And there's a lot of domains where that matters, be it health records, which are still pretty much captured in natural language, be it legal text or contract text, or data extracted from social media. So there's lots of applications where text still plays a role and data is just unstructured and needs to be interpreted. Right? And this is basically what, this is kind of the area that transformers these days form the backbone models of what's basically considered state-of-the-art. So this is where they come from. Another thing is that transformers are getting bigger and bigger. So in the intro, Julian already mentioned BERT, which happened in 2018. And you can see that X is the timeline here and Y is the model size. You can see that transformers are actually getting bigger and bigger, and they are the largest models that we have in AI these days. And you can see that this is basically logarithmic scale, right? So this is not linear growth, but this is exponential growth in size. And so basically what you do if you scale these models is you find out that that quality improves with capacity here. It's not quite clear where the limit to this is. So this is actually subject to debate, if we just need to scale the models further or if we need to add a little extra grain of salt here. But well, this is kind of the trend that's going on right now, right? And if you think of models like GPT or Megatron as your regular small research group around the corner, you usually don't even have the hardware to operate these models. Like even inference becomes tricky, but training them becomes pretty much infeasible if you don't have very specialized large-scale GPU hardware. So if you want to try out these models, here's just a small opportunity to do this. So I actually like doing that from time to time. On playaidungeon.io, you can find a text adventure. So the older ones among us may still know what this is. It's basically kind of an interactive story. And this is being told by an AI here, more precisely by GPT, which is one transformer model, obviously. And the AI will ask you to pick a genre for your story, pick a name for your character, and then it will interact with you in a text-based fashion. So you have the opportunity to do stuff or to say stuff, and then the AI will respond with a bit of text and basically generate a story. And so if you come from NLP research like 10 years ago, it's pretty impressive how well this text is generated. So if you look at that in detail, it's not only syntactically correct language, but the AI also, it picks up actions and objects that are mentioned in the story and comes up with reasonable consequences from certain actions or reasonable things that you can do with certain objects. So we look into how do transformers manage to do that. So one last motivational slide. So if you want to apply your transformer to your particular problem, what do you do? So you basically need to train a model, like with most machine learning models, you have to do that. And with transformers, you will do that in 2 stages. So there would be a pre-training stage and a fine-tuning stage, which is typical for deep learning. And so the pre-training stage basically happens on a large text corpus, usually beyond 1 billion tokens. So you can think of this as Wikipedia training on that, for example, or training on an even much larger pile of text that you crawled from the web somehow. And from that, you bootstrap a so-called self-supervised learning task. And self-supervised means that you don't give the model anything but the text. So there is no additional labels or stuff like that. And from that, you bootstrap a learning task and you conduct a large-scale pre-training, which can take several weeks. And in this pre-training, the model tries to pick up kind of how language is structured, like which words are synonyms to one another, which words typically follow other words, and so on and so forth. And the task by which you usually pre-train is that you take out certain parts of the text or modify certain parts of the text, and then you train the model to correct these mistakes. And this is the way that the model adapts or adopts the properties of language. So this is really expensive. So this takes usually multiple weeks on multiple GPUs, depending on the corpus size and your pre-training problem. The good news is that these days, these models are shareable. So if you want to use a transformer for your particular problem at hand, there's the option to download it. So for example, there's the library Hugging Face, which has kind of a model zoo with lots of pre-trained transformers that people uploaded there. And you can just download your model from there and then fine-tune it to your particular task, usually in a supervised fashion. So usually you would have target data, which can be small scale. So you can even think of just a few sentences with corresponding labels. And then you would take your model and basically add just a few output neurons corresponding to the classes of your target problem. We would call this usually a head model. And then you fine-tune the whole thing, and you have a model that combines the strength of the transformer to model overall properties of language with the application-specific decision layer. Yeah, so this is how you typically would proceed with applying transformers to your problem at hand. Right, so much about motivation and how you would apply transformers and how people use them and what they use them for. Next thing I want to do is kind of give you a brief impression of where transformers come from and how they came to be and what problem they actually try to solve by their architecture. So what's actually our key goal is natural language processing to be robust. And this is illustrated by a very simple example here. One thing we want to be robust to is paraphrasation of the same semantic content. Right? So basically, if I have some AI model making some decision about a piece of text, I want this decision to be robust with respect to different paraphrases of the same fact. And that's illustrated here, right? So if I input the sentence, I really love the movie, versus I deeply enjoyed the film, I basically want the AI model to output the same decision, even those are entirely different words, obviously. So what you actually try to do is you try to come up with some kind of encoding, which is represented by these things here. These are supposed to be vectors or so-called embeddings by which we represent these words. And what would be pretty great is if really and deeply came with the same embeddings, which I would then feed into the AI model. And obviously, that makes the job of the AI model much easier if the input already indicates that these terms are really, really similar. Right. So this is actually our goal. We want kind of robust embeddings that indicate that things are the same, even though they look really, really different. So people looked into that for decades, and in 2013 to 16, the approach of the time was to use so-called word embeddings, which means for each word in a base vocabulary, we would learn basically a fixed vector. And this leads to stuff like here on the one hand side, popular methods at the time were word2vec or fast text or glove. And what they would give you is kind of embedding or word clouds, so to say, because an embedding is basically a point in a high-dimensional space. And then I can get illustrations of these word points. And one thing you observe if you train these models is that stuff that's similar ends up with similar embeddings. All right. So, for example, pepper and salt have similar positions in embedding space. Things like baking, boiling, and cooking. So these embeddings have been extracted from cooking recipes. So things that you do basically come or occupy a certain region in embedding space, and different kinds of meat occupy different regions, and so on and so forth. On the right-hand side, you see another interesting properties of these things, namely that semantic relations between things emerge as shifts in that embedding space. So this has been an embedding trained with company names and with their CEOs, and you see that there's kind of a constant shift that leads from a company to its CEO. And that kind of indicates that the embeddings might be definitely interesting for reasoning about text in a sense. Right? So this was the generation of models before. So what's the severe limitations of these static word embeddings is that words come with different meanings depending on the context that I use them in. Right? So here's an example. Let's think of this as a high-dimensional embedding space. And actually, if I take a word like jaguar, there are different meanings of the word, and it's kind of, not really suitable to use just a single vector to represent all of them. Yeah, so a jaguar might be the wildcat or the car, or this is Trevor Lawrence. He's actually the quarterback of the Jaguars, so he's also called a jaguar. And this problem, this is super common. So if we think about the other words illustrated here, I would argue that basically all of them may have different meanings. If you think of the word rolls, this may actually be third person singular of the word roll. Mercedes might be a name. Lion might be the chocolate bar. Fox is a slang word for an attractive woman, and so on and so forth. Brown is a color. Even stuff like Bentley, here you could argue that this can refer to the company or to its product, the car. Right? So basically, lots and lots of words are ambiguous in text, and there's many, many examples for this. So what I just listed were homonyms, words with different meanings, but there are other examples for this. For example, coreferences. Yeah, if you think of the word she, that's basically a placeholder for some entity that's mentioned in the text, and it's kind of a shortcut. And we as humans can resolve which entity this refers to, but the machine has no notion from the word itself. Another example, one of my favorite ones, is that phrases make words interact with one another. Right? So this is actually something from my personal experience. So my daughter was kind of 3 years old, and I was combing her hair, and I told her to hold still. And she kept on moving. And after multiple arguments, we realized that she didn't understand the phrase, but she thought that hold still means be quiet, because still means also quiet in German. And she didn't know that she wasn't supposed to move, right? So this nicely indicates how words act on one another, right? So the meaning of the word still is modified by the presence of the word hold in the surrounding. And so basically the core mechanism of transformers is really about, capturing this interaction in a neural network. So basically what transformers try to do is they try to contextualize these word embeddings. That's illustrated here. So the idea is that I feed an input sentence into the encoder, which will later be the transformer. And for each word, there will be an embedding, like a static embedding for Jaguar, which is not sensitive to the meaning yet. And then the neural network processes this embedding sequence and gives me a better one, a so-called contextualized one, in which the other words in the sentence have been baked into the representation of Jaguar, and the output embedding will clearly indicate that this must be about the wildcat. Right? So this is that's actually the goal of transformers. And there's been a boost in research and these models feeding on text blocks and contextualizing them. And there's many, many works on different varieties of transformer models. What they have in common is that they're all based on one key mechanism called attention. And that's what we'll look into next. So we'll look at the nuts and bolts of transformers really and try to understand this attention mechanism. So before that, let's briefly sidetrack to different neural network models that people have been used for the issue before. So if you know a little about neural networks, you've certainly come across recurrent neural networks, for example. So these would basically feed on an input sequence one by one, and they have kind of a memory cell that captures everything that the network has read so far. And then you would consume this sequence word by word, or token by token. And usually you would do that in 2 passes, once forward, once backward. And obviously, if you do that, you would come by the word spotted here, in the backward pass, you would capture it. And in this step, you would combine spotted and jaguar, and you would capture the information that it must be the wildcat. Right? Because spotted is kind of the indicator word that acts on jaguar. Another option that people have tried is convolutional neural networks. So they have been popular, very popular for images, and they work internally with filters. And you can apply that to text as well. So here the idea would be that you basically shift filters across the input sequence. And the filter, when placed here, for example, could capture that there's the word jaguar 2 words apart from the word spotted. And the filter could combine this into a signal that outputs that this is actually about the wildcat. Yeah? So both these models could contextualize embeddings. The thing is, why they don't do that so well is illustrated here. So I've brought you a little bit of example text, and our goal would be to contextualize this here, the language. And so basically, we would like to find out that the language is actually French, what's being mentioned here. And you see in the text that, well, it's kind of long, right? I used to live in France, close to the western coast, blah, blah, blah. It took me 20 years to learn the language properly. And the keyword that I need to contextualize language is actually very far apart. It's France, right? And so the thing is that words in a text are rather loosely arranged, and far off words can influence one another pretty strongly semantically. So, and both recurrent networks and CNNs are terrible at modeling that. So these long-term relationships. With RNNs, the problem really is that they need to carry information through the sequence step by step. And from this, there results this problem of vanishing gradients. Experts know about that. And with CNNs, the thing is that filters are limited in scale, and it's a fixed arrangement what filters are targeted at. So it's not really flexible. So what attention does instead is it's super aggressive. It basically says everything can interact with everything. That's illustrated here. With attention, so we basically distinguish between a target sequence, which we want to produce, for example, and a reference sequence, which we can use to produce. And one typical example for this is actually where transformers come from, is machine translation. So here you would have a reference sentence in English, for example. You want to produce a sentence in German. And with attention, so now our goal right now is to produce the next word. And attention would look at all words in the reference sequence and kind of compute a weight, which of these words matter. So right now, for example, we might complete this with als wir aus dem Zug stiegen. So the next important words might be got out. And very is actually not important right now. Right. So, and one variant of this, which we will focus on right now, is self-attention. So here the target sequence and the reference sequence are actually the same. So this would be, the goal of contextualizing Jaguar right now. And for this, we could, again, Jaguar could attend to everything else in the sequence here and kind of find out that fur is what mattered and appear maybe didn't matter so much. Right. So we now want to mathematically kind of model this attending step, and this is the only formula I'll throw at you in this talk. But this is kind of the key attention formula. We'll briefly look at that and try to dissect it. This is how an attention layer looks like. So it basically uses 3 input embeddings. So you can think of this as a layer in your neural network. It takes embeddings of the tokens in the sequence, so Q1 to Qn, and one of them is our Jaguar, and the others are fur and bush and so on and so forth. And there's not only one embedding for each word, but there's 3 of them, namely queries, keys, and values. And So let's look at what this formula now actually does with these embeddings. So basically, the core of attention is what's happening inside these brackets here. So this is a matrix multiplication between the query embeddings and the key embeddings. So basically, each green thingy here would be one embedding for one word in our sentence. Let's say the sentence is, I carried a watermelon. And there's a similar matrix K for the key embeddings, but I transpose this such that it's not rows anymore, but the embeddings basically become columns. And then matrix multiplication is rows times columns. And this will lead to a 4x4 matrix here. So which means basically I compute a scalar product between each word's query embedding and each word's key embedding. And this is kind of a similarity matrix, right? So it will tell me for each word in the sequence how strongly it attends to other words in the sequence, right? And this matrix basically carries these attention scores. So then we divide by the square root of the dimensionality of the embeddings. That's just a normalization step. The next thing is that we apply a softmax. So for those who know it, this is basically something that turns these raw scores into probabilities. So basically, I now have something like a score telling me that the jaguar attends to 70% to the word spotted, for example. And then the third operation is the multiplication with the value embeddings, and that's basically a weighted sum. Right, because again, it's row times column. So basically each of these embeddings gets a particular weight and flows into the new embedding for each term in the sequence. So for Jaguar, for example. Right, so it's fairly simple. We compute similarity scores or attention scores, and we use them in a weighted sum. That's what attention really does. One thing to keep in mind here, and that's actually very relevant for practitioners, is that computing that is not super cheap. So obviously, if I have a sequence of length n, I need to compute an n times n similarity matrix. So this is squared in the sequence length that I input into the transformer. And n squared is not super cheap. It's like a bad sorting algorithm. So this, you can use it in practice, but its scalability is limited. So in practice, you can use transformers with 1,000 tokens or a few thousand tokens, but you cannot take a long business report of 80 pages and just feed it into the transformer and have it process it. Yeah, so it just becomes impractical at some time, at some scale. And there are ways around that, but still there's not the accepted solution to make transformers scalable yet. So if you want to use them, you always need to chunk your text into rather small pieces. Okay, so now we know one key layer in the transformer. Obviously, transformers now are big networks, which means we're in deep learning here, right? So these are deep networks. And with deep learning, the mechanism really is that you stack layers on top of each other. So the input of layer number L feeds, so the output of layer L feeds as input to layer L plus 1. And so people tried that for images first. There it was really successful back in 2012. And the effect that you saw is that the first layers would do simple stuff. This is an illustration of a deep CNN, and you can kind of see that in the first layer, the network detects greenish stuff, diagonal edges, green to black edges, and so on and so forth. And in layer 2, the network starts to puzzle the signals that it gets from layer 1 together to more complex features. So basically, if you take an edge like this and an edge like this, it forms a corner. Right, and you see that cornerish things start developing here, or things that correspond to very thin structures. And if you do that for a couple of layers, you get really amazing neurons that output really very diverse, semantically accurate features in the image, like unibikes. Don't even know how you would call that actually, or flowers or text. Yeah, so basically, if we stack layers, we can combine features to more complex stuff. And in text, you kind of observe similar things. So this here is now the most famous, earliest illustration of a full-fledged transformer. And you see that there are things here, so-called transformer blocks. They are stacked on top of each other n times. And n is typically like 12 blocks on top of each other in early networks, up to almost 100 blocks in later networks. So basically, we stack transformer blocks. And people inspected transformers and found out that a similar thing as we see it for images happens here as well. Namely, the bottom layers of the network, the early layers, they tend to model simple NLP tasks. So, for example, part of speech tagging, finding out if something is a noun or a verb, right? That happens in the early layers. And more complex tasks happen in the top layers of the network. Right, so let's have a brief look at this transformer here. So what I actually explained to you right now in detail is this orange box here, the multi-head attention. And we have a lot of stuff around that. So there's more feed-forward layers, there's multiple additions. Also, what I can't go into detail here, what you actually feed in the transformer, so how the pre-processing looks like, and so on and so forth. There's a lot I couldn't cover, but let's just leave it with that. One thing that's remarkable here is that this thing has two columns or two components. On the left-hand side, we have a so-called encoder, and on the right-hand side, we have a so-called decoder. And they're both combined. And that's actually the last content chapter, which addresses what the difference between these stages is and what you get from combining the two. So let's start with the decoder. What is this about? So you can think of this as a transformer now. And so one way of training this transformer is called left-to-right language modeling or autoregressive language modeling, which would mean that the transformer is always trained at predicting the next word in a text. Right? That's illustrated here. Basically, when training this thing, we would feed it a sentence, and at each point in the sequence, the transformer would try to predict the next word. Like, my name is probably Bob. Something like that. If you want to do this kind of training, it's obvious that the transformer, when predicting Bob, should not look at the next token yet. Right? So if you tell it that the next token is Bond, then the task obviously becomes trivial. So what we do instead is we allow attention only attend to the left. So the transformer may always just look at tokens to the left of the current token. And with this type of transformer, so with so-called decoders, you can actually generate text. But what you cannot do is to look at context to the right. So it's kind of limited in the quality of its embeddings. And the most famous type of these models, called the generative pre-training transformer, the famous GPTs that you have seen on the news from time to time. Yeah. So here a little bit of just something that we did in Wiesbaden. So basically, when GPT-1 was a thing at the time in 2018, we trained one in German for ourselves. So to our knowledge, there wasn't a German GPT at the time. So we thought, hey, let's build one of these models ourselves. So we really pre-trained one. We used almost all our GPUs we had at the time, which was 8, trained the model for more than 3 weeks. And we did that on a pretty decent corpus containing Wikipedia and German novels and a bit of news text. And you see, so one thing you observe here is that the model almost did not overfit. So the training loss kept on decreasing, validation loss kept on decreasing as well. And this model is far from trained yet. So we could as well have trained it for another month, and probably quality would have even been better. We needed the resources at the time. And what you can then do, let's skip that, is you can prompt GPT with the beginning of a text sequence, and then the model can generate from that. Yeah, and what was pretty funny at the time is that depending on which prompt you would give it, it would generate different texts because it had been trained on lyrical or novels, basically. So if you would give it as a prompt, so heiße doch, it would produce text like that. If you would give it the beginning of a Wikipedia article, like this here, it would basically hallucinate a Wikipedia article. And if you would give it like a news beginning, it produces news, right? And you can see from these examples here, the model is not perfect. So if you read it, semantically, you find out that it doesn't really make sense. Like here's dieselbe Distanz is being mentioned, and the same distance hasn't been mentioned before, right? So it's still not perfect, but syntactically, and if you look at the individual sentences, it's actually pretty plausible already. So this is good generation quality. From models these days, you would get even better. So the second type of model that you could apply, if you like to, is the encoder. And the encoder you would use if you don't want to generate text necessarily, but you would apply the encoder if you want a good representation for text to feed it into a decision model. Because the thing with the encoder is you allow it in training to look to the left and to the right. GPT cannot do that. And you would typically train it by taking something out of the input sequence and have that, fill in. Like you would take out this word here, might have been used the force loop, and the model is supposed to predict the word that's missing here. And to do so, it can attend to the right and to the left. Most famous example here is BERT. So it's been a couple of years, but it's still a decent model. There's bigger ones, there's better ones, and more efficient ones these days. But BERT was kind of the thing that was in the news pretty big. So bottom line, if you want to make some downstream decision, use an encoder, something that's bidirectional. And then there's so-called encoder decoders, which combine the two. Right? So this would be a model which takes some input sequence, like text in one language, here in English, and translates it to another sequence. This would be Gaelic, I think. And this model kind of combines the encoder on the left-hand side, which is supposed to produce cool representations for the input text. And then the decoder uses those as an additional signal, right? Because we do not want to generate arbitrary Gaelic text, but text that matches the input sequence. And there's famous examples of that. Most famously, probably T5. BERT was another thing. So these you typically use if you solve sequence-to-sequence problems. Machine translation is one. Another would be summarization of text. Yeah, so you give it a huge text block and you want a short summary out of that. You would do that with a sequence-to-sequence model too. Right. So a bit of criticism in the end. So what are the limitations of that? And why are transformers also subject to controversy? So one thing is that transformers still are just replicators of patterns that appear often in a huge scale training set, right? And there's this thing called the semantic gap, which refers to the fact that some things just do not manifest in text because we as humans know it and nobody ever writes it down. Or it's just not being communicated because the speaker and the listener are both aware of the fact. And so people played around with GPT-3, which is, one of the famous transformers, also one of the biggest ones still. And so GPT-3 could not answer this question here, like how many feet fit in a shoe. So everybody's aware that the answer is 1, but GPT started to produce gibberish, right? So it wouldn't simply reply to the answer, but it gives out some dialogue because it's just, it's a text producer. Nobody tells it or constrains it what to produce. And it even mentioned 10 here. So even if you want to grab the answer from here, it's actually wrong, right? So GPT cannot answer this simple question. And that's a huge part of criticism. Traditional linguists basically say that this is all bullshit, right? And we think more about how humans actually make sense of text because we contextualize things, we put them in context with the mind map that we have. And all this is kind of part of a black box, which we don't really understand. So this is what people don't like about these transformers. Other points of criticism are the cost and the CO2 consumption. So the biggest models like GPT-3, they're, even for us, they're too big to run this on our GPU infrastructure. So it's basically the tech companies can do that, right? And there's huge costs that come with the development of these models. So even, I don't even know about the latest models, but there have been estimates that training such a big transformer comes with CO2 costs that correspond to multiple lifespans of a car. And one training run may not be too expensive, but if you combine it with architecture search and hyperparameter search, where you need to run the same model over and over again with a lot of trial and error, there's substantial cost to that. Third thing is bias and discrimination. So if you play the text adventure that I mentioned above, and if you, input a sentence that might indicate something romantic or erotic, you may notice that suddenly the transformer actually starts to produce porn. And people discovered that with this text adventure, and it's, companies been criticized for that. And that's because transformers basically replicate what they see. And if you train it on bulks of text that you just got from the internet, this is not curated text at all, right? So there may be discrimination effects, there may be bias effects and so on and so forth. So much about that. Still, so if I have another 5 minutes, we keep on working with transformers despite these points of debate. And finally, a bit of an ad block about stuff that we do in our research group. So if you're interested and you see some hook points there, feel free to contact me. So LAVIS is basically Learning and Visual Systems. That's our research group in Wiesbaden. So I brought you 2 things basically that we work on, or 2.5 things. One thing is that we also employ transformers for information extraction from documents. And so here's an example for that. Let's say we have a document here, like a small passage of text consisting of 3 sentences. And with information extraction, you want to find out multiple things here. First of all, you would want to localize where are spans in this text that describe entities, right? Like the New York Times, Manhattan, Henry J. Raymond, and so on and so forth. The second thing is that you would like to resolve coreferences, because entities are not mentioned once in the text, but they're mentioned multiple times, and not always with the same name. So basically, the New York Times has been referred to here 3 times, and we would like to cluster these mentions. That would be step 2. Third thing is we would like to type things. So basically, we would find out that this is an organization, this is a person, and so on and so forth. And fourth thing is that we actually want to extract facts. And often these are modeled as binary relations, like that the person here is the founder of this organization. And so traditionally, you would have covered these steps with different NLP models. So there would be one model specialized in finding entities, one model specialized in determining relations between them, and so on and so forth. So what we are interested in is to built an end-to-end model, so one that addresses all these tasks in a multitask fashion. It's supposed to do that on document level, so not only on sentence level, but really on documents where things are mentioned multiple times. We need to address all these tasks at once. Right, and this is one area that we were active in. So here's two of our papers from the area. One is one model that we developed is BERT, which solves multiple tasks in an end-to-end fashion. This is still a model for feeding single sentences into, and its extension we call Gerex, published that 1 year later. You can actually find both of them on GitHub. If you ever want a cool information extraction model, just go there. It's been starred multiple times, 450 stars right now. It's been forked pretty often, so it's also a state-of-the-art result. So it's if you want to look into that, that would be cool. What we also look into a lot is not only doing this on research data sets, which are typically crawled from Wikipedia, but we run projects with application partners interested in particular domains. For example, from insurance, from banking. And here's a third example from another project that we had on technical service. So here we basically had a partner. They were interested in maintaining machines. And what would happen there is that a technician would be sent to a malfunctioning machine. He would repair that somehow. And after that, he would describe the problems in a ticket and the solution. And they had collected more than 1 million of these tickets. So it seems like pretty often there's stuff wrong with these machines. And in these tickets, there's a lot of knowledge. And now an inexperienced technician comes in. He's supposed to solve the same problem again. So basically, we have a search problem here, right, on an uncurated corpus of text. So, and here we applied our technology to localize interesting entities, finding out where they are located relative to each other, and which problems exist with which kind of entities and which solutions you have. Right, so that you can use information extraction particularly for that. And the interesting thing with transformers here is that you don't even need huge annotated training sets for that. So usually if you have like 50 examples of an entity or of a certain type of problem, that, rule of thumb is that might suffice for a pretty good model, actually, because the transformer actually has captured all the properties of language in its pre-training, right? So another thing we're interested in is code infilling and code search. So these are all applications where we could use that technology to support software engineers or developers. Yeah, because at its core, code is basically text that you write. It's a sequence of tokens in a sense, and you can apply transformers to that as well. Often code is also accompanied by text, like comments, maybe other documentation that you have. So you can apply the transformers here as well. And people might be aware of stuff like GitHub Copilot or Tab9. So there are actually already products which you can give a bit of code, and they will try to fill gaps in that code. Right. So we're running a project actually this year and next year called Codebuddy that happens with your neighbors from ROE actually. So they are partners in that. And the goal here is to combine infilling and search. So basically what things like GitHub Copilot do so far is that there's this huge model which will fill a gap in your code, and you don't really know where the model got that from. Right, so the GPT has been trained on a lot of code on the net, and it memorizes it somehow in its weights and biases, and then it copies it over into your code. But you don't really know if it's correct, and you don't really know where it comes from. So the idea in this project is to not build an intransparent infiller, but to couple this with a code search. So you would basically give our system the piece of code that you're writing right now, you would point the system to the gap. Hey, I need to fill in this. And maybe you would say, hey, I want this to happen here. And then we search for pieces of code in your knowledge base. Like you can think of this as your company repository, for example. And you would find pieces of code that are relevant and helpful to fill into the gap. And then there would be a second component that actually uses the code that you say is relevant and then fills it really in. So that's kind of our mission statement here. Right, so maybe as a last slide, this is one recent work that we looked into. So basically, if you want to do that, what you need to build is a code retriever. So what you want to do is you take multiple pieces of code from random GitHub repositories, and then you cut out certain parts, like the green part here, and then you train the transformer to find the green part given its gray surrounding. Right, so that's what we want to do. And so the problem with this is that you have several clues by which you can find out that the two match, but these clues are not really semantical clues. So for example, you can use the fact that the same identifier, cursor, appears in the two. Or you can use the fact that they're indented to the same level. And basically, so what we did in this work is we apply pre-processing to kind of obscure the green part from the gray part, basically by masking out variable names, by dedenting the code. And by this, we kind of made sure that we trained a meaningful retriever model that really finds stuff by semantic. Okay, so I guess that's pretty much it. So thanks for listening through that. I managed, well, not quite in time. I hope it was interesting nevertheless. You find me here, and I'm open to questions. So thanks for having me.
Well, thanks for giving this great talk. I immediately did have a question at the beginning that basically I had different points during the entire talk where it kept coming up. So, like the end you talked about code. At the beginning you talked about health and legal texts, and I think that came up in between. There's the project by GitHub that also focuses on code. There's, I think Google does DocAI, which focuses sort of on legal and contracting data, where they try to extract entities from that. Is there a specific kind of text that lends itself better to, especially to entity extraction? Because it seems like the more structured, like code, like with a logical structure that text is, it seems, maybe that's just the bias of people developing the AI models, but it seems that seems to be the target for AI more often to me. Maybe you can have some counterexamples if that's not the case.
You mean extracting entities, you mean, or?
Yeah, and maybe processing by AI in general, but yeah, specifically, like the example that I keep coming up with is extracting entities from legal text seems like a thing, and then reasoning about code seems to be a thing, and reasoning about health data seems to be a thing right there. So there's, I don't know, maybe I'm seeing a pattern that's not there, but it seems there's specific types of text that lends itself better than maybe prose, for instance.
Yeah, so I think when it comes to health and legal tech, I think these are just, super interesting application areas because, you need to read a lot of text as the expert in the area. Like legal search has been around for like ages as an information retrieval problem. It's one of the most ancient ones and actually most widely used in practice. Obviously, you struggle with, the fact that medical text, for example, is obviously really different from text that the transformer may have been pre-trained on. But the pre-training data sets also get more diverse and diverse. So if you look at pre-training data sets, it's not just Wikipedia anymore, but these days people mix source code and code scraped from the web and Wikipedia and novels and pretty much everything in there. Also multilingual. So if you look at BERT, for example, already in 2019, I think could do multiple languages. So I guess you kind of rely on the model just, to be kind of trained on everything. And it's so big that it can switch modality, right? So if you apply it to text, it will switch into this mode and it's able to recognize entities there. Yeah. I think that's kind of the strategy, is make the model bigger. So.
I think I saw several YouTubers make videos about GPT-3 when that was sort of the big game in town, and they fed it scripts and they fed it, I don't know, titles, like past titles of their own videos to kind of mine it for video ideas, stuff like that, which was kind of entertaining on the one hand, and it was surprisingly, semantically it was relatively sound, syntactically definitely. But then again, the consensus that I felt the community had was, yes, it's already pretty good, but it's obviously non-human. It's still very like the context that you spoke of, right? That's just missing, and there's just information that machines don't really currently have access to.
Absolutely right. So I think the huge gap that AI faces is this. The gap between applications where, gaining 5% gives you a business model somehow, and it's valuable, like search, for example. If you can give people better hits, everybody's happy, but, nobody dies if the number one hit is a bad one. And the gap to safety critical applications, in a sense, where the model really needs to output the right stuff. You might argue that health maybe goes into this direction. Self-driving cars, obviously, from a different domain, other point. And in programming, it's pretty much the same story, because, the model outputs something it's kind of intransparent. And if you look at it, it's, you might put something in your code that's incorrect because you didn't really check. So, and I think it's not, it's not quite there yet. If you look at this text adventure, for example, or if you look at the code that GPT produces, stuff that's kind of standard, which you see often in GitHub repos or you see often in text, is pretty good at that. But there's, you still always run into these situations where you register pretty easily that this is not a human producing that text. Yeah, and it's so the question is how much cherry picking is going on here, right?
I don't want to monopolize you with my own question. So Michael Bukowski asked a question. Could you shortly dive a little bit deeper into why fine-tuning of pre-trained models makes my results better instead of just using the pre-trained model? Thanks.
Yes. Do people still see my slides? I think so, right?
Yes, I think so.
Thanks. So just going back to the beginning of the presentation. So I think it refers to this year, right? So the two stages with pre-training and fine-tuning. So the thing is, what you see in, so let's say your transformer is a 20-layer model. Then what usually happens is that the first layers of your model will tend to do stuff that's generically useful. And if you come closer toward the end of the network, you will find neurons that are really specialized in just solving the pre-training task, which would be predicting the next word, right? So, these neurons are really just, they're good for solving the pre-training task, but they're not good for solving the target task anymore. So what you usually do is you kind of chop off the last layer, or you can even chop off more than that, like the last 2 or last 3 layers. And then you just insert like a new untrained layer, and you would train that. And usually if you train, and by that you adapt the model to your problem at hand. So if you don't do that, the model will just still output the next word, right? And then there's the difference between... Yeah, sorry, please go ahead.
No, I didn't want to interrupt you. I was just having a follow-up epiphany question.
Right. And just, so one more remark there. So there's the two options. Either you just train these red edges here. So you just train the network that, or the layer, this head model that you add, and just train these red edges here, or you really fine tune into the transformer and also adapt the structure here. And so it's just an empirical finding that, so it's really a necessity for the transformer to, oh, sorry, I'm actually running out of,
running out of juice on the laptop.
Here. Give me a second.
Yeah.
So it should be better now. So sorry about that. It's just an empirical observation. So if you compare this transfer learning, where you just train the added edges, and fine tuning, where we really train the whole model, fine tuning usually works much better. So you could argue that the transformer can understand the basic language when pre-trained, but it needs more adaptation to your target task, really. So there's not enough neurons to solve your particular problem at hand yet.
So that's probably the answer. I was going to have a follow-up question, but I think you answered it, and that was my epiphany moment just a second ago, where I was wondering, wasn't there an additional additional danger of overfitting? But of course, if the problem is that the model is too broad, then overfitting is not really the concern, right? Is that correct?
Yes.
Okay.
Well, I think with language modeling, what you see, if it's a huge corpus, so it's usually pretty stable, and we didn't experience much overfitting there. If your target data set is small and you have, then overfitting is an issue. So what you typically want to do is you want to split your target data into different folds and do cross-validation, like you always do it in machine learning, and then stop training after, as soon as performance decreases on the validation set. So that's that's kind of the standard thing, and you need to do it in fine-tuning. And I've seen very different behavior on different target problems. So sometimes overfitting doesn't seem to be an issue, and sometimes you really need to stop after 2 epochs, right? So,
okay.
So
Michael
no universal wisdom there.
Michael also gave us a perfect answer. Thanks, especially the chopping off part. That seemed to really explain the question very well. Okay, so thanks. I do have a bunch of different other questions, but I think maybe they're a little too specialized for the Tech Talk right now. So for now, thank you very much, Adrian, for your great Tech Talk. Very interesting stuff. I think we could go on hours and hours talking about this. For now, I don't actually know what the next topic is. I don't think we have announced it yet, too. So I'm going to leave you with a mystery for Tech Talk number 64, rather, which is a power of 2. So stay tuned for that.
Big one.
It's probably going to be very interesting. Yes, it isn't set. I just talked to Paul before this, so stay tuned for that, and see you next time, hopefully. And again, thank you very much, Adrian.
Yeah, thanks for having me. Bye, guys.